Hello everyone, I'm Kang Heechan. Today, I'll explain the concept of topological insulator. Topological insulator is the combination of the word topology and insulator. Well, it does not sound really familiar. So, let me explain the concept one by one. First, what is topology? Topology is a mathematical study of spaces and structures in terms of position. When a geometric object goes under continuous deformations, such as stretching, twisting, crumpling, and bending, not tearing or gluing, which are not continuous, the properties are preserved. Topology is a mathematical concern of these behaviors. Let me bring up a single example. Imagine a deformation of a circle. When we deform a circle into different shapes, such as a diamond, a triangle, rectangle, an ellipse, and a star. This is possible in terms of topology. They are called topologically equivalent. Let's look for different case. Can we deform a circle into a donut shape? Well, I guess not. Making a hole is not continuous deformation. So, they are topologically distinct. Different shapes having single hole and zero hole, like the example, it is called that they are in different class of topology. Okay, now, what is an insulator? Basically, we know that insulators are nonmetals, which are non-conducting materials. But it is not an accurate definition. Let me bring the concept of band gap. Band is the range of energy levels that electrons can exist. Valence band is the highest range of energies where electrons can present at 0K. The outermost electrons sometimes leave valence band and become free electrons. Conduction band is the energy level which has lowest occupied energy level for conduction electrons. Fermi level is the energy level which is occupied by the electron orbital at 0K. It is normally in between conduction band and valence band. For conductors, both conduction band and valence band overlap, so electrons can freely move to another state, which makes conduction. For insulators, there is a band gap between conduction band and valence band, so electrons cannot freely move to other bands. They are localized. In this video, we are interested in these insulators. Now, we are almost aware of simple meanings of the word topology and insulator. Before we understand topological insulator, we should know what quantum Hall effect is. Here is an experiment explaining the Hall effect. We have thin electrical conductor current sending to it. When we introduce a magnetic field, the charge flow is disturbed due to a force called Lorentz force. And there is a new voltage which is perpendicular to both current and magnetic field. It is called Hall voltage. There is a graph of resistivity of the conductor when we increase magnetic field. For longitudinal resistivity, rho xx, it is constant. Transverse resistivity, rho xy, it linearly increases as magnetic field intensity increases. However, same experiment for 2D electron gas in extremely low temperature and strong magnetic field, the result of resistivity is quite different. First, longitudinal resistivities were not constant. It shows some peaks. Transverse resistivities increases as magnetic field intensity increases, but the relation is not linear. It's like a stair shape. Scientists found out that there is a quantized relation between resistivity and magnetic field. Furthermore, quantum Hall effect is observed even without strong magnetic field. It's called quantum spin Hall effect. The key is spin-orbit coupling. Spin-orbit coupling is the coupling of electrons' intrinsic spin and orbitals' momentum's degree of freedom. Spin-induced force is possible without strong external magnetic field. In the experiments, there is a phenomenon that electrons moving along edge. For quantum spin Hall effect, either way of movement of electrons, clockwise and counterclockwise, is possible by up and down spin. Let's look at the energy momentum graph. Usually, insulators have band gap, so electrons could not move to another band. But results of the experiment tells us that surface conduction is possible even in insulators. Now I think that we have enough information to understand the topological insulator. Topological insulators are quantum materials have both properties of metal and insulator. Energy band gap in bulk shows insulator properties, and continuous energy level on surface shows metal properties. Let's bring quantum Hall effect experiment again. For typical insulators, electron movement is localized. However, focusing at the edge, it seems like electrons are moving in single direction and make currents. It shows conducting properties even though it is an insulator. Normal insulators cannot overcome Fermi level, but topological insulators are not. Conduction is happening at the surface, even still the bulk is an insulator. Therefore, topological insulators are useful in many fields using this phenomena. We can use topological insulators in quantum computing, superconductors, transistors, and lasers. Many research possibilities still exist. Hope this video is helpful for understanding topological insulators. Thank you for listening.